Hello everyone. So this video is about a course I took from Skyfi Labs known as Machine Learning for Beginners. It's a pretty good course to get you started with machine learning. I learned the most basic and the very first algorithm you will stumble across in your journey, that is the simple linear regression. So what is linear regression? A simple linear regression is, I would say, just a straight line. So what's the equation of a straight line? Y equal to mx plus c, right? X is your input, y is your output. So simple linear regression lets you predict this y based on the input x. Also, these m and c values are important to get the best value of y, right? So what we're doing in linear regression is we're finding the most optimum values of m and c, so that we get the best possible value of y for an input x. This is what linear regression is about. Anyways, so this is, I would say, all the prerequisites. We use NumPy, Pandas, Matplotlib, sklearn. This is important. This is the Boston housing dataset. So what we're doing in this, what's the aim? The aim of this code is just to find or predict the price of a house based on features. So we have 13 features in this dataset and 506 samples. Out of those 13 features, we'll be using the best possible feature to predict the output. We'll see it later. So we loaded our dataset. This is our dataset, Boston housing, and like I said, it's got 13 features, 506 samples. So these are all the features: crime rate, then we've got age, dis, rad, tax. These are all the features. This is the table. Alright, so now we made a data frame of target. What is this target? Target is just the required value or the required output. Okay, min max of the target. Now here's what we did: we concatenated features with target so that we get a table which consists of features and target listed right in front of it. So we have this target in front of features. Okay, now here comes the interesting part. We're using Pearson correlation for this model. So we've got 13 features. Out of these 13 features, we have to choose that feature which gives the highest correlation with our output, that is highest correlation with the target. We're just finding correlation between attributes, like those are the features, 13 features, the correlation between those features and our target. This is the correlation graph. As you can see, LSTAT shows highest correlation with our target. So LSTAT is the feature we'll be going with for this algorithm. Let me tell you what this absolute does. We're not concerned whether our feature is inversely correlated with the target or directly correlated. In inverse correlation, we get negative values of the correlation coefficient, but we're not concerned with that. So if you remove this abs, you'll get to see negative values as well. So these are the values of correlation coefficient. CRIM shows 0.38 correlation coefficient, and out of these the highest is 0.737 showed by LSTAT. That's why we'll be using LSTAT for this model, because LSTAT shows the highest correlation with our target. Okay, now what is this X? X is our input, Y is our output. Of course, Y is your target. The values of LSTAT will be your input, right? Because it shows the highest correlation with our output. So we just print the first 5 values of both of them, and as you can see, there's these values are not scaled. Like, we see a sudden jump from 4.98 we went to 9.14, and then we went to 2.94. So it's really hard to work with these spikes. So what do? We scale this data and reshape it such that it fits in -1 to 1 range. So after reshaping, we use fit transform function and with the help of min max scaler. So we scale our data such that all the values fall into -1 to 1 range, just like this. Alright, so first 5 values of X, all between -1 to +1. In the same way, first 5 values of y all between -1 to +1. Next up, according to a rule in machine learning, we partition our data set into two parts. 80% is your training data and the rest 20% is your testing data. Next come our error, update and gradient descent functions. I would say these three functions are the heart of this model. Without this, this model will be lifeless. Anyways, so this is the error function. It takes x is your input, m is your slope, c is your intercept, and t is the output. These four values are the arguments for this error function, and it calculates the mean squared error. This is the formula for the mean squared error. Okay, next up is the update function. This takes the same arguments as error, but we have learning rate as an extra argument in this. So what this update function does, like the name suggests, it updates the values of m and c. So for example, if you had a value of m which was not that good for the model, it'll update the value of m. It'll give a new value of m which will be better than the previous one. So we're updating these both values. And next is our gradient descent function. We pass initial values of mc, we pass training data set, we pass input, this is the output, learning rate, number of iterations and the error threshold. So we initialize m with initial value of m and c same way, and now we generate two empty lists named error values and mc values. For loop will iterate these number of times. Okay, iterations are the number of times we want this for loop to iterate. So we're calling error function. Error function is called, it'll calculate the error, it'll return the error, and then we check if error is less than error threshold. If it is, then we found the best possible values of m and c. So we break through the loop, we append this value of e to this empty list error values, and then we got m and c. We call update function. Like I said, update function updates and gives the next best value of m and c. The update function will be called multiple times until we have an error less than the error threshold, and then we return all these values. Here the initial value of m which we sent in here was 0.9, initial value of c was 0, learning rate was 0.001, number of iterations 250 and error threshold 0.001. We called gradient descent function here. We passed all these values as an argument. It generated output. These are the outputs mc. These new m and c are the optimum values of m and c. Okay, we got error values, we got mc values combined. Now this is the value of m, this is the value of c. So m, c, and this thing goes on and on. Now here's the part where we visualize our data. You can see our model fitting to the data set. Let me just show you. So this was previously the initial values of m and c and the line formed with that, and with each iteration our model fits into the data set. Okay, as you can see, it's fitting, and as you could see in the last few iterations there was not much change. This is our model fitting to that. We just saw our model fit the testing data set. And this is the final model fitting to our testing data set. Now we again created a scatter. This time we're using the training dataset, and this is our output. So I would say it's a pretty good fit on the training dataset as well as on the testing one. It's not a bad fit. And then to visualize the errors, we again plot a graph of error versus iteration. So as you can see, with increasing number of iterations our error is decreasing, and that is something we actually wanted. We want our error to be minimized. And like I said, in the last few iterations you couldn't see much of a change, right? It looks the same because the error value is constant after a certain number of iterations, hence we don't see much of a change in the last few iterations. Okay, so y equal to mx plus c, it's the same. This is your y, this is your x input, m and c. Y equal to mx plus c. Then you calculate the mean squared error between the testing value, the ideal value which should have been your output, and the predicted value, the one predicted by a model we used here. we calculated here, and it's 0.019, which is not bad, it's decent. And here we create a data frame, and you look at this table. This is the X, your input, this is your target, that is the ideal value, and this is your predicted Y, which your model predicted. And as you can see, there's not much of a difference in these values, pretty close. Some values which might not be perfect, because no model is 100% accurate, right? Testing dataset, it's the same we did here in the green one. We worked in the range of -1 to 1, values from -1 to 1 in real life, right? And hence we need to rescale these values to their original scale. We reduce the scale to -1 to +1. Now it's time we get back, so we use inverse transform. Last time, to rescale this to this range, we used fit transform, but we're using inverse transform now. We create another table, and this is your input, again ideal value and the value predicted by a model. We should be getting this value, and we are getting this, which is not too far, they're pretty close. The same way, for this input should have gotten this value, and we're getting this value. Again, not much of a difference. Again, this is pretty accurate. So I really have to thank Skyfi Labs for launching this course. It was a pretty good, pretty decent course, nice for a beginner, good enough to get you started with machine learning. Thank you for watching.